We just directly go to the statement. Okay, so the topic is Menelaus theorem. So just like Ceva's theorem is trying to capture collinearity of lines, sorry, of concurrency of lines. Ceva's theorem shall capture concurrency of lines. This is about collinearity of points. Okay, so this is trying to capture, sorry, this is trying to capture collinearity. So when are 3 points on the same straight line, how could you say that in terms of ratios? Okay, collinearity. So let us begin like this. So we have this triangle, and then we have three collinear points. But that just means a line, right? We have a line passing through the triangle. So it will obviously intersect two of the sides, but it will not intersect the third side, in the usual sense. You see, it doesn't intersect the third side in the usual sense. But just to make sense of it, we say it intersects the extension. Not a problem. Is that okay? Yeah. So we have a triangle, and then we have three collinear points. So earlier we had three concurrent lines coming out from the vertices. Here we have three collinear points on the sides. Okay. So this is a point. Let's call this point D. Call this. So we want to say this. We want to say basically what this implies in terms of ratios. Yeah. The question is, what does this imply in terms of ratios? Like we said, when we have three concurrent lines. What does this imply for the ratios? We had kind of discovered it in the situation of from the situation of concurrent lines itself. But would someone like to tell me what can we say about the ratios, or how we had seen it in better? But at least what can we say about the ratios? I mean, the ratio of the pieces once again, AD, DB, I'm essentially just asking you to state the Menelaus theorem, at least one side of it. Okay, as some you would remember, right? So it's basically similar. So we have AD, and in some sense, this is a more useful tool than Ceva's theorem. If one looks at directly from a calculation perspective, calculating, I do AD by DB times, so I have to do two more products. What should they be? Come on, someone tell me. Oh, sorry, can you say louder? Okay, my mic was, yeah, say. AE by AC, AE by EC. Okay. Um, mhm. BC by C. No, not BC by CF, but something similar. Let's see if AE by EC is the right thing to say. AE by EC. Is this right? And then what should be the next thing? So basically, we are looking at the ratio in which the point is dividing that line. Okay. So D is dividing AB into AD by DB. E is dividing AC into AE by EC. So I mean, whether it should be EC by AE or AE by EC, that one has to still decide. But here is the important thing. F, the point F is dividing the line BC into what ratio? How does one make sense of that? It's outside, right? So here the ratio is whether it's that or 1 by that, that's a different question, but it is at least BF, or from F you go to B, and then from F you go to C. Just imagine, right? If F was somewhere in between here, you would have done that, right? FB, BF, FC. The way in which F divides a line. When F is outside, then also we make sense of it like this. Okay, you go FB and then FC, like you would if F was. So this is the external division, whatever there are. This you will see also. You can call it geometry. But then I mean, it's certainly that these are the ratios as I've written one of them there, and then other one here, or other one also, and then. But what should be the order? That is important, right? That has to be said. How does one decide that? So let's say that debate. Why? Huh. So you can. That is a decent way. I agree, right? If you go kind of go cyclically, you have done AD by DB, so then you go right, and then you go up, right, and you go CC by AE. That's one way to think about it. But another way is just that what it's like, which one are you picking first, the left or the right one? Okay, so it's like I'm just saying these things are just a way to remember this basically. Also, just to also see that these are conceptually things, it's fundamental that they're not arbitrarily, the directions are not arbitrary. Um, but if you look at it like this, if you if you look at it like this, right, from here, then AD by DB means you're picking the left and then the right. Yeah, you're picking the left part, the left segment, and the right, then the right part, and then the right side. That's AD by DB. So you're choosing left and then right. So then when you come to AC, then you have to look again from outside AC. That's that, outside the triangle. Again, if you do, then you look left and right. What's the left now? Now C is left and A is right. So it should be EC by A, EA, or whatever. So that's why it should be CE by EA. Yeah, you can remember this in any way you want. Better to keep something consistent. Because this is the same way in which I had said about C. You can see it by cyclic or left also, I suppose, will work. And then similarly here, then left and then right, so DF by. Okay. Ishana, does the left-right analogy help you to decide the last one? FC, BF, FC, which one? the order. So basically, so it will, right? Because you can imagine the rep is inside. So your analogies all will also work. So as you can see, this not some, that the way I've said it, you can do it. But it is important to be sure. Just memorizing it will not work. Okay, it's important to develop a scheme for yourself and just make sure that it works. You may say, why I'm saying this point so again and again, it's so boring. But the point is that when later on you go that we are not doing now, and that's the point of way I'm trying to teach this. I'm not doing these theorems in full generality. Neither have I done Ceva's theorem. Okay, usually, I mean, later on, and I hope you guys will, you will, um, that you will go on your own, go there on your own because not everything can be taught. There's no time. Like you will meet situations, for example, the Ceva's theorem only, since you guys are more comfortable with that. You will meet with Cevians which are not inside the triangle at all. Line is going like this from the vertex, this top vertex. Then a line is going maybe like this. Okay. And then you'll have a line going like this. These three are also Cevians. These three are also lines from the vertices. Because are they intersecting the opposite triangle? And you would know, yes, they are intersecting the opposite triangle. I mean, the opposite sides. Their extension, they're extending, they're intersecting their extensions. You see? So that's a. So this is A. This is the intersection point. It's outside. Okay. Similarly, C is also intersecting here. E. And similarly, this one, I mean, I should maybe make it red, but whatever. You see, now you have to extend the Cevian also. It's also intersecting the side, right? G, F, maybe this is, yeah, this, so this is D, this is, so this should be F, yeah. Anyway, so see, it's already gets complicated. So I'm not asking you to, but then here you would need a consistent scheme. Otherwise, you will just get lost. Like, what should be the order of the ratios? What should be the ratios? Okay, so you would have to decide on that. So for that, you have to be clear about the scheme, and you have to be clear about, okay, what does it mean when I'm taking the ratio? What does it mean? Okay, the idea is to see in what part does it divide the segment. If it's outside, then also I can make sense of dividing the segment. If you're clear about those pieces, then you can patch it up and you can go on. Ceva's theorem for triangles, then you will do for quadrilaterals and so on. But they're not doing. That's why be clear. Don't depend too much on just have a look. Okay, this is the order. So Google it, look at the order. You can do that, but you have to also make sure you develop your own style. If it's consistent, then it will keep working. Good. So this is the theorem. Now we have actually already seen this theorem, and I just go over that. How we saw it. And all of these come from drawing the right parallels and parallelograms. Drawing parallel lines, one can understand these results. So we're not going to do a proof of this because the assumptions we have already done it earlier. But I just show the situation in which we had it. So that you can see that it's kind of, it always is there. Whenever there is concurrency, there is collinearity there somewhere. So we had, I'm just going to quickly draw all three with the same. We had this thing, and then we studied the concurrency. Then we were just wondering, I mean, we gave some numbers. This is 2:1. Then this will now become 1:2. Then when we did that, we were wondering what is the area of each of the triangles. And we were able to figure that out. Is that right? What is the area of each of the small triangles? Maybe the whole triangle area is 1. What's the area of each of the small triangles? Okay, for the big triangles, easy. Like this one, yeah, there's 2/3 of the whole thing, and this one is 1/3 of the whole thing, and so on. But we ask for each of the small triangles, and we were able to figure that out. Once you figure that out, x, y, z, w. No, once you figure out those numbers, you, okay, then you can figure out what is. Then we kind of figured out what is this ratio, this by this. That's what we figured out. Okay, what is this by this? Okay, and then I'll just draw picture similar here. I'll call this the C. Okay, let's call this F. You can see the similarity between these two pictures. Okay, once we figured out, let's call this, then we checked and we saw that AD by DB, AE by CE, and no, okay, AD by DB times EC by CA, and some third ratio, okay, BF by MC. That we saw that time because two of the ratios we already had, right? A third one which we found out by just by application of Ceva's theorem, right? By knowing that the product is one and figuring out the small thing by algebra, that ratio. We figured out that it was the product was one. We got this. Okay, so we already have this theorem. Okay, we're not going to prove it. We already have it. You can try this. I mean, to prove this even here, right? You can say, yeah, I'll complete the triangle. You can say, yeah, I'll just complete the triangle. I'll take this triangle, I'll complete it. Good. And now I'll apply Ceva's theorem. Right? You can apply Ceva's theorem so you know the relation between these ratios. And then again, a small triangle, then you will find AE by EC in terms of BCCF, ADDB, and you'll see the product. Okay, that is the idea. I'm not proving it now. It's very related. And for a formal proof, for a different proof, you can look at challenges and thrills or anything. They will drop some perpendiculars and do. You can do it in English. But let's not go into that. We want to look at the converse of theorem. So let's believe this. If you were not there that time, I've just given you an idea. Okay, you can try this on your own from here. You can go back and look at it. Okay, yeah, go back and look at that, or you can try it. But let's move forward. At least you know the idea. Let's try to get the converse. That is important. Yeah, so let's first do the converse, then we can look at products. So what is the converse? The converse is you have 3 points. You have 3 points and you have this ratio given. Okay, such that this is given to you. You want to show that the 3 points are on the same straight line. That G, F, R, okay. So now let's think how this. So again, we contemplated last time how to show that 3 point three lines pass through the same point. We showed that, right? And we also basically thought of how to show that, how to show such a statement. Yes, yeah, that's so. Let's assume. Okay, so let's write here. So just but remember, somehow we have to apply the theorem itself to prove the converse, just like we did in the Ceva's theorem case. Right? To prove that the lines were passing through the same point, right? We kind of said, okay, you take one of the lines, which was and take the second line, E, and let's say F was not passing through the point. We say, okay, let's take the line that passes through the point, and we showed that this ratio of that line, which that line creates, is the same as that what F creates. Right. And then we showed that then it means not showed. Then it just means that these points are the same. We have to do something similar, but you just think freely. I'm not asking you to have to think like this. So just think. I'll just okay. Yes, that's right. So let's just say that the F was not there, okay, and take some X is there. Okay. So assume they are not collinear, but you would still want to create a line. Do you apply the series to apply the Menelaus theorem, right? So you assume they are not collinear. That's the situation. Then X is the. So we have created a collinear situation. To prove contradictions in geometry like this, you have to create that situation, okay, of collinearity or concurrence. Okay. Yes, so you can apply the Menelaus theorem, okay, and get that AD by dB and whatever convention you want, you get, yeah, and you will get x xc. Yeah, is that right? No, left first, right? So xb by xc, this is equal to 1. This is what we got. But you remember that this is also what we already have. Maybe this is also true. This is also true. And this is also true. Both are true. Yes, right. So you get that xb by xc is equal to, you can see it in any way, fb by fc. So this implies that they are the same. Okay, this should be, I suppose it should be clear. Okay, is it clear, or is it not correct, or what is it? Yeah. But you have to maybe say that f is outside, x and f are outside the outside BC. Then there can only be one such point. Is that right? So what I'm trying to, because this is can be a simple point. You take a straight line, this straight line, and let's say you fix 2 points, you're fixing BC. And let's say I ask you, give me a point x such that xb by xc is 2. But you see, you can give me 2 points actually. Yeah, one of them will be inside, it is somewhere here. Is that right? And one of them will be outside, somewhere here. But you guys agree, right, that there can be 2 such points. So again, there are 2 such points such that this can happen. Okay. So basically, the point x and the point x prime, or the point x and f, and I don't want to call it x and f because they're both outside, but the point x and x prime, they have the same ratio, they divide BC in the same ratio. One of them divides it internally, the other divides it externally. Okay. So these 2 points are similar in nature. Should be xb, x prime b by x prime c. So you get 2 points. But if you know that both of them are outside, then there can be only, then there cannot be both. It can only be 1 point. If you know that both are outside. Okay. These x and x prime are tremendously important. These pairs and x and x, these pairs x and x prime, which are dividing BC in the same ratio, one internally and one externally. These are called harmonic conjugates. These are called harmonic conjugates. You will meet them a lot when you do projective geometry. Even if you're doing some advanced Olympiad geometry, you will need this. You will know why I'm saying advanced. Yeah. Let's not say anything more, but these are called harmonic conjugates. They are harmonic in a certain sense. It's taken from music notes. Yeah, you can also be, it can also be written in harmonic progressions. But you guys see that there will be 2 such points. That is the point. If one outside, one inside. That's important. But yeah, more about that. So this is fine. This is done. But let's say that you got this wonderful point x, right? You got this point. You have this point x, or let's just call it f. So the theorem is proved, right? Because we have shown that. But there is a little more, and that can be made into a very interesting questions. There is a point f that is outside. If I ask you, can you give me that point f prime which is inside, which has the same ratio? So you have the point f and you have this ratio, right? Bf by fp. by FC. Can you give me a point inside which has the same ratio? There will be, right? You know that there will be a point inside also. I mean, where it will be, it will probably be somewhere here. I don't know. But can you construct that point by some geometric method? If you think about the Ceva's theorem, it also gives you a similar ratio. I mean, if D and E were featuring in the Ceva's theorem somehow, then also you would have this ratio AD by DB and EEC by AE, right? And then you would have a third. This, I mean, you can just take it like this, right? It's just extending the imagination. Then what will that point? No, but two lines are always concurrent, right? I'm just saying these two lines, right? Two lines, right? But then this F prime, if there was an F prime, or rather you can just imagine, if there was a line from here which was passing through and going, let's call this T, then this T will have that property. Right? This T will have that property that this is 1. And then you get it right by Ceva's theorem. Because already this part appears in both Ceva's theorem and Menelaus theorem. I have to put it, comparing it at night there, right? But the third part that appears in the Ceva's theorem is inside the line, inside the segment BC. But in Menelaus theorem, it appears outside the segment BC. But the ratio is the same. Okay. There is a T, and this T is the answer, right? Because then TB by TC is the same. Just look at this equation and this equation. And BF by FC is same as TB by TC. And that's your harmonic conjugate. So from this point F, I've got this point T. Isn't this is very wonderful, right? I mean, you see, so we have made this construction without using any compass also. And this construction just comes, yeah, right? It's natural. So 3 points are given, make that 4th point, which has the same ratio, divides the first 2 lines, first 2 points with the same ratio as the 3rd one. Figure out that 4th point. You can figure that out like this. But again, something more interesting is happening here. This question was not even about this picture at all, not about this at all. It is just about these 4 points. Rather about only 3 points. Just imagine, right? Initially, you just started with 3 points. I mean, this question that we have kind of solved about finding that 4th point. I mean, you started this question with just like this. Started this question by taking 2 points B and C on a straight line. I mean, just making a line segment joining B and C. Then you put a third point on the line, and then you ask me to find a 4th point which has the same ratio as the 3rd point does with respect to the first. Right? You put the 3rd point and you had FB by FC. Then you asked to give me that 4th point which has the same ratio inside. I mean, that's all the question was initially. I mean, that's how it can be seen. But then we make this huge, we made a triangle, we made a huge picture. It says something very interesting. So maybe that you don't see now, but I'll just say this. It says, so let's put it like this. What I'm trying to say is, suppose now, if I mean, to answer this question, you have to make a triangle, right? You have to make this triangle ABC. To make this point, choose the point A, you have to make this triangle and then do this construction, right? But couldn't you have chosen any other triangle? Uh, Forget about any other triangle. Couldn't you have chosen any other line DE instead of DEF? Why not, right? You could have chosen any other line from F to make this construction. Isn't that right? And you would have done the same construction, but you would have got the same point. That is almost seems like sounds like a miracle, but it is true. Okay, so here it does not look true because because that line, the blue line is not a straight line. Okay, because that's my blue line. Okay, I've drawn it in that bad way. Yes, but if I draw it properly, then even here in Zoom, it should be like this. And no, no, I think the blue lines were wrong, not D. These blue lines were wrong, right? But see, D cannot be wrong, right? D is just so let's take some steps back. Yes, yeah, right. D, sorry, yeah, right. So let's just take one step back so that everybody can understand. Yeah, that's right. T is wrong. That's the right way to say it. So initially we had to find the point T, right? Now to find the point, let me use a light stroke. To find the point T, you see, we appealed to the Ceva's theorem. We said, okay, you join this to create a concurrency type situation because this kind of situation comes in there, and then you have this. But I mean, this line DEF is not special. That's what we realized right away, right? Because this question initially was not about the line. You can make any other line like this and do the same thing. You should get the same point. Take the intersections, and you do. You see, I'm this new point that I'm getting, this new intersection that I'm getting is on the same line as this one. So you will get the same T in the end, and you should. How can you get a different T, right? You should get the same T. Is this, yeah, is this making sense to others? So we had to find the fourth T, but if I would have asked you, if you would have asked me to find the fourth T directly, I would have not been able to do it. But we kind of stumbled upon it, right? We had this picture, we had this line, we knew Ceva's theorem, we kind of were trying to make, okay, is it right that there is a unique, just asking a very simple question closely, right? Is there a unique point F? Oh, there can be a point inside also which has that ratio. That's how we came. Okay, then how do we find that point? Then we said, okay, we can apply Ceva's theorem to find the point in this situation. But that point T is unique. It shouldn't depend on this triangle or the line. And so you make any other line and it should give you the same point T. And so you should get this beautiful picture. I think this is so nice. And you can do even more bizarre, right? You could have even changed the point A in the sense, right? You could have taken a completely different triangle and done the same thing. You would have got the same point T. You take a completely different triangle, you make this, and again you make the crisscross and you join it. You'll get the same T. I'm not doing it here because this is this. That point T is so invariant under so many things. It's invariant under projective transformation. But that's how it's called. So that's why it's harmonic conjugate is a pretty rigid thing. It's actually not a ratio. It's not more than a ratio. Okay, it's even when you change your perspective, if you take this figure and you look at it from different perspectives, that T doesn't change. That is the point. It is something like that. but you will be using these things later, but now this construction can be asked as an application of Ceva. Anyway, so let's come down to more regular stuff, because we have to be able to do some simple questions with these things also. So there's one question, this old RMO type questions. This appears in every area where any questions come. So what I'm giving is not the exact question, but and we have solved this kind of question with a lot of work earlier, and now we will see that with this theorem, even the harder versions of this, or rather more layered versions of this, the area the same. So yeah, let's say that we have this line and this line. Just 1 second. Never mind. Let's just. Yeah, so we have this picture. We have A. C. Let's say that D is the midpoint. Let's keep the numbers easy. So let's say that D is the midpoint. And let's just also assume that this is a trisection. So let's assume that this is a trisection. And I have asked this question up here, but kind of we did an easier version of this because let's do it. Let's do this. This is equal. Okay. What we want to find is area of XYC. You can put the area of the what to find on this page. Let's see now with our current tools, is it easier, or even how do we even do this? It's like revisiting a harder version of an old question. So think, what ratios do you have to find to attack the problem? What ratios should I focus on? Right? And then can I use this theorem to find them easily? If I don't use them, then how do I? So what ratios should we find? That is the question. then you can apply the theorem, right? Or we can just apply the theorem direct, go on applying the theorem to different triangles in this thing, different situations in this configuration, triangles and lines. That's another thing. But here it is relatively clear, I suppose. Right? What ratios should I focus on? So, see, you already know that, and this was the idea earlier also, that you zoom in, basically go into that triangle XYZ step by step. In the sense that DBC is that subtriangle kind of. DBC is understood. Its ratio, the ratio of its area is understood. It's half of the whole triangle, right? So now we can focus on figuring out what is XYC compared to DBC. Is that right? We could focus on what is XYC, what is this compared to DBC. Right? And then you would just make half of this. So you would take this and you would make half. So you just focus on the XYZ by DBC. So you see XYZ and DBC, they have the same base DB, right? So the question that really comes down to is what is XY compared to DB? Right? Because XYC, the triangle XYC and the triangle DBC, they have the same base. So you have to figure out what is XY, so XD, YD, like that you have to go. Okay, so let's do one thing. Let me just make the question slightly easier for us. What if I just put it like this and I ask you to find XDC? The idea is the same. Ask you to find XDC. This doesn't even need the Menelaus theorem, but you can use it to do this. So if you just figure out what is XB by XB or DB or something like that. So how can you apply Menelaus theorem to do this? Or even without it if you want? You have done this question earlier, but yeah, I just change the orientation a little bit. Here the E is not even important here, okay? E is not important. Exactly. A by fx, y. What does that mean? Okay. Yes. Mhm. Okay, so we apply the Ceva's theorem. So AF by FB, this we know is 1:2 times exactly C times CT by GA is 1. And so we can find BT by TC. That's 2:1, right? Okay. So we're applying Ceva's theorem to find out, but how is it useful? See, is it useful directly? Okay, you can always use it. But then you'll end up computing something outside, right? Like you join F and D and you connect with something outside, then you'll get another ratio, but again, that's not directly useful. That's right. Something outside that ratio you will get, but that's not directly useful. I mean, this itself, what you have done here, PT by TC, this itself can be used, right? In the sense that this is 2:1, so you know that it is something like, so BT by TC is 2:1, right? So you know that if this is 2 lambda, then this is lambda. I mean, this area of those small things, right? That's also 2:1. And then if this is 2 beta, then this is also this beta. And if this is alpha, then this is alpha. And you can again set up some more equations, right? And you can actually find answer. Is that right? And this already will do the problem. Okay, you can set up some more equations. But but that is fine. That's something that you have already done. Right? So we want to do this problem more directly. That is the whole point of knowing this. So we don't want to find this t and then do it. That's so suddenly that's like doing the proof of Menelaus. So how do you find the xt by xt directly? Because we have proved the theorem once. You know the theorem, we don't want to apply the whole proof again. So you see, when you want to find a certain ratio on a certain line, right, you have to see what lines are passing through that point. FC is the line. Yeah. FC is the line that is passing through that. Right? And you have to consider BD as the side of one of the triangles of your interest. Right? My point is that the triangle that is interesting is the triangle ABD. If I look at the triangle ABD and I look at the three collinear points, okay, but not ABC. I'm not looking at ABC. Okay, I'm looking at ABD because the ratio I want is on BD, not on BC, right? And the line that is passing through there is only one line which I can use. And the other point of the decision is ABX. Just naturally, this is the line. Now apply the Menelaus theorem in this situation. Is that making sense? Yeah. So ABD is a triangle, and now you want to apply the Menelaus. And there are 3 points which it is cutting. So it is cutting the side F at, sorry, it's cutting the side F at, it's cutting the side AB at F, it's cutting the side BD at X, and it's cutting AD at C externally. So what will be? The right term equation for the Menelaus theorem. So we already applying it in a strange triangle, not a correct. Yes, AC is right. Yeah, right, left, right, and then left. AC by AD. Not by AD. That has to be CD. Yeah, CD. Right, good. It's CD. And then what's the last one? XC. How is XC coming? No, the triangle. You have to look at the triangle. The triangle is ABG, and you have to see what is the ratio in which this line cuts the sides of the triangle. You see, so for F, you told me that F is cutting the line AB at into two AF and BF, AF and BF, right? You've said it that. Then it's cutting AD externally as AC and CD, but X is cutting BD, right? Yes. Okay. Is it making sense to everyone, right? The X is cutting BD, is not cutting something else. So that's the thing. I mean, this you can apply Menelaus theorem in many ways in the same configuration. You could actually look at some other triangles and apply it. But the point is, you have to be clear. What is my triangle? What is my line? Two things. The triangle is ABG and the line is FX. Right? Okay, the line is FXC. Those are the 3 points. So you have to see how they divide the corresponding sides. Hear about that? You cannot go wrong. Okay. And then from here you can find XP by XP. I think we need a little more practice in some simple questions about this. Okay. So the other question that I gave, let's not do that then. You can try that later. Okay. If you're comfortable with this, you should do that, certainly. It's very easy to say. So you can hear it is done. So you can note it. I'm not going to discuss this now. And I want a smaller one. on this middle one. So this is a challenge question. You can try. Will you able to do it now? But let's just do some one or two routine questions and then end it today. Because yeah, this is the thing. You have to get comfortable with this. And the challenges, the thrills has some difficult questions. Just give me 1 minute. Certainly, there are questions available online here and there, but the problem is that they quickly go into difficult questions. So I have a source. This is called. I have mentioned this book earlier also. Oh, I don't have it here because it's an old laptop. So let me just get the book. In the sense, I'll also look at the questions. There are some more better questions, easier questions, I suppose. And or if you look at any, yeah, I'll leave it. I'll just find the question and ask you. It's basically in that. What I'm saying is that book, Ceva, the geometry revisited. So beautiful, very very nice. So from there you can see a few more complicated questions. But I'll also do a few. More quickly. This applications of this theorem comes up all the time. I've seen it several times while discussing with other students in simple exams, AMC, AME, some MCQ problems here and there. It just keeps coming. Okay. So I had a few here which I want to discuss. So let's just do this. Let's not do the last day's question. Let's just quickly do some basic problems. Good. So there is this one question. So this is I'm taking this from Brilliant. This is you obviously know. So let's discuss one of them. Yeah. And one can make up many questions also. It may become difficult. So from the vertex C, it's very easy. Suddenly there are mosquitoes here. It doesn't happen. Right triangle. So from the vertex C, from the vertex C, height CK is dropped. A vertex C of the right triangle ABC. So ABC. I'm confused because then the vertex CK. Its language expression is very strange. Let's just do this question. Think about this. I just inside a figure, I think is there in tomato also. So this is the thing. Nothing much is given. This is just this region has area 3. This region is area 6. This is area 4. Want to find the area of the remaining region. Got it. Very elegant. Want to find the area of the quadrilateral. You can think now it's like a problem just to try it. Let's see, just try it. Of the points on C. Yes, yes. So let's call this P. So using this without using any theorem as such, PP by PC is and similar. That's because 3 is to 3, 6, 3 and 6 are the areas of the base length. And similarly, this is a new piece of information. 2 is to, this is 3 is to 2. Uh, you can try to divide that quadrilateral into 2 triangles, and then ADB, yeah. Okay. And with the line EPC, so we can just take, you can consider these 3 points. Right? It's hard to maybe think of it how to do it directly, right? But you can divide this up into two, and you can try to find out the two of them. So, yes, right. But let's just write it. Let's write it and see. So if you apply it in this case, you get AE by EB, and then you get BP by PD, and then C is the point that is dividing AD externally. So it should be CD by CA, and this we know is 1. So BP by PD we know it's 3:2, right? So then this AE by EB, which is the ratio we want, and CD by CA, which is another ratio we want, this is 2:3. Okay, this is one round application of Ceva Menelaus theorem. What else could you do? Mhm. Right. So let's extend this line. So if you extend that line, then you can try to use Ceva's theorem. Then but you'll again get some unknown ratio. I mean, I don't know. It can be done from here also. From there. But if you think in a more straightforward way, see, you want to use the ratio EP is to PC, which was observed right in the beginning. EP by PC, you want to use this ratio. If you want to use the ratio AP by PC, or EP, sorry, EP by PC, ABT. Okay, let's see. Yeah, ABT. If you do ABT, then what happens? ABT is the triangle ABT, you're saying? Yeah, obviously. And then what line? What line? That is important. So, sorry. PD. EC. But if you focus on EC, then it's okay, but then it will not be useful in the sense, right? Because you don't know AP by PD, AP by PT, and neither do you know anything about this, right? So I mean, you could still do the problem, but see, if you want EP by PC, then that has to be one subdivision, right? That has to be one of the subdivisions. So that EC has to be a side of one of your interested of the triangle you should be interested in. Do you get my point? Yeah. This has to be the side of a triangle. So I mean the natural triangle which I can see in the picture, which I should look at, is AEC. Yeah. One could also say BEC, but BEC is not so nice. AEC is better. Because when you look at AEC, then obviously you look at AEC and the triangle AEC, and you have to look at the 3 points D, C, B. Right? Because in this it's very good because you know that D is dividing the point AD into this ratio, which you want to find, and it's dividing EC into this ratio, which you know. It's good. And you are getting this ratio, right? It's dividing AE. B is dividing AE into a ratio AE by EB, right? Something like that. You'll get an equation which will again have the same two variables, AE by EB and CD by CA kind of thing. You have two equations and two variables you can solve. But let's just finish it. So let's try to finish this. Let's do it properly. Good. Let's finish this. I just plug in the charger. This whole laptop, it just gets discharged very quickly. I might get disconnected while doing it, so just just try it. I just come. Okay, so let's see. So what do we get when we apply this theorem to AEC with the points GP and D, GP and B? At least that we should write first. Right, CD by DA, and so you are writing that as, I'll take that as left and right. So that's one of the sides. Then we come to the side EC, right? And there again you look left and then right. So it's 3 by 6, so that is half. And then you come to the side AE and you look at how B divides it. Okay? And that will be AB by, and that is 1. So from here, as Ishan has said, this will be AB by AB. Yeah, AB, AB by AB. I mean, these two equations, I mean, these are the same things, right? So AB by EB, you can write that AB by EB, that can be written as 1 plus AE by EB. Okay. Okay. We have two variables, two equations, so we should be able to solve. It's already solved in this. So you'll get CD by DA, and then CD times DA times AE times EB. This is already 2:3. Okay, so from here you find out CD by DA. Nice, now. And then you know AE by EB, so you know the, you know this because this is 3. So knowing this ratio AE by EB, you will know this. The wonderful thing, right, is application of this. So you figure out the right lines and the right triangles. Okay. That's it. So there are some other questions. I'll just send it to you guys after the class. And yeah, I think we'll stop here. Next time, I think we will not continue discussing these. Okay. If you have doubts, please ask me though. Okay, I would like to clear it and discuss it. But Monday, I want to go to a new topic. We have done some. There's much more always. That's always there. But we should pause this topic. I believe we already developed basics, and now it's up to you how much you can try problems, read, and try. And for the sake of time, we'll move to a new topic. So on Monday, I'll move to pigeonhole principle. Okay, I'll be trying to follow the book Vivaldi. As I've said, you can download a PDF or you can just buy it. It's very useful, very good book. All of the book is fantastic. So it's not just for that one chapter. All of the book is fantastic. As I have discussed enumerative combinatorics from that portion with some of you. So it's a very wonderful book. It's also a officially recommended book, I suppose. Okay. So, I don't Olympiads, I suppose. Yes, I don't know, but definitely in the yeah, in this exam. But principle. So Arthur Angel is there, problem solving strategy, but that's more difficult in the first book. So we'll follow that book and also maybe something from mathematical circles and other things. So that's the topic we'll do on Monday 9:30. Hope positively. If it's 9 or 9:40, okay. So are there any questions for today? If there is, then just ask me. Ask me now. It's better to ask now than while up.